This is going to be a fairly informal session, and please stop me if you've got any questions or comments or input. That would be great. What I've done is I've put my slides up online on a OneDrive, so if anyone wants to, you can scan using your phone, so you've actually got access to the slides there. I'll show it again at the end as well. So just a very quick intro. I'm not a mathematical statistician. In fact, I'm a very reluctant statistician at all. When I first started my psych degree back in the 1970s, yes, I am that old, we all had to do statistics as part of the psych training. It was compulsory. And I hated every single minute of it. We had a Russian mathematical statistician teaching us, and I'm still not sure what his face looks like because he scribbled on the board all of these mathematical theorems and formulas and got very excited, saying, as you can see from the following formula, which of course none of us mere mortals had a clue what he was doing. And the universe has a very strange sense of humour, because when I graduated as a psychologist, I was 21, I looked about 10, and no one would employ me despite a first-class honours. So the university took pity and they hired me as a tutor. And what subject did they hire me as a tutor for? Statistics. So I had to translate the Russian mathematical statistician's work into something that 200 very scared psychology students could understand. So that was my first introduction to teaching stats. And I thought once I finished there and actually got a job as a real psych, that I would never have to do it again. But of course, roll on 15 years, I did my PhD, and there were the stats still waiting for me there. So I actually threw myself into it and did a fairly statistical PhD. This was at the Faculty of Education at Monash Uni, and got dobbed in to teach all the research methods and the stats courses. So I had to write up notes for my students because there was no good stats books around. They were written by the Russian mathematical statisticians. So I wrote a cookbook. Basically, it was like, you want to cook chicken, soup, or you open the book and here's the recipe. Here's the ingredients, here's the procedure, and this is what it should look like. And it turned out that my notes were dobbed into a publisher and it just took off. So it was sold initially in 2002. I think it was its first edition, and then got raffled off to overseas publishers, and it just took off. So about 1 million copies, I've been told, have sold worldwide. It's in about 4 or 5 different languages. So it's funny how something that I just prepared for my students has become so popular. I'm still not a mathematical statistician. I had to, after it was all published, I decided I better go and do a stats qualification. So I enrolled at Swinburne Uni in the mathematical statistics department to do a Masters of Stats. But a few months in, I had a tap on the shoulder and the dean asked to see me. And they were looking for someone human to teach statistics to people who didn't want to learn statistics. So I actually hurriedly finished a grad cert and then became a statistics lecturer. And my life's been sort of statistics and research ever since. So very strange process that we go through to get who we are. So what I want to do today is basically just go through some of the basic statistical principles and just translate it into English. Have a look at some of the commonly used stats that you might see in journal articles, and just think about the analysis process when you're doing a quantitative study. What I'm aiming at is people who don't like statistics. And in fact, many of the students that I've had have actually been terrified, particularly when they've been forced to study statistics and they need to pass it to actually go through. So this is my funny little sort of slide that illustrates how many of my students feel when they first start doing stats. So basically, from my point of view, stats is just a way of organising chaos, that there's lots of numbers and we need to find how we can use those numbers to tell a story. And that story needs to be standardised so that researchers across the world can actually be doing the same sorts of procedures. So that's the way I view statistics, just as a tool. Unfortunately, and I'm sorry if I offend anyone, but many of the statistics language that's around was developed by male statisticians back in the 50s and 60s or earlier, who were trying to make big names for themselves by making the words as complicated as they can be. So I think the jargon that's used is one of the barriers that people have to understanding statistics. That, coupled with a love of formula and equations, I think is enough to scare a lot of people off. So I promise there are no formulas in this presentation. In fact, these are the only formulas that exist in this presentation. So I'm not explaining anything mathematically. Everything will just be in terms of examples. So the word variable, of course, comes in a few different flavors. We've got independent variables, which is our predictors, and we have our dependent variables, which are the things that we're trying to explain. So in my research as a psychologist, I was interested in how a lack of control was related to stress. And of course, there's the old one of, does money bring happiness, as an example. So what we're doing is we're trying to tell stories about the population, but we're using samples. So when we're referring to the population, a characteristic, it's referred to as a parameter. And when we're talking about what we find in our sample, it's called a statistic. Once again, it's just terms. People go, what's a parameter? So that's just a quick explanation. One of the key things we need to look at is the level of measurement. So when we're designing the study, we need to design it with the statistics that we want to do in mind, because if we only collect data that's categorical, that is discrete, unrelated groups, then there's a limit to the type of statistical tests that we can do. So the level of measurement come in about 4 different flavors. So nominal is where you have categories that are unrelated. Ordinal is where we have discrete but ordinate categories. And then the next two, which is where statistics really comes into the fore, is interval level measurement and ratio. So we're looking at equal distances between values across a wide range. For interval, we don't necessarily have a clear 0 point, but for ratio, we do. So they're just the 4 levels that we need to keep in mind, because every statistic I talk about later will be only appropriate for particular types of measurement level. So when we're thinking about the level of measurement, the type of stats that we're going to use can be either appropriate or inappropriate. There's been a few theses that I've read as an examiner where they've talked about the mean score for sex. So if sex is scored 1 and 2, and you have a mean score of 1.2, it doesn't mean anything, but some students don't necessarily understand the numbers that are being pumped out by SPSS. If we want to use some of the more powerful statistical techniques, then we really need to think about how we can measure our data at an interval or a ratio level. So for instance, if you're interested in the effect of age on some sort of outcome, don't just ask people to tick a category, actually ask for their actual age, because it makes a big difference in terms of the statistical tests. Now, the proviso there, of course, is a lot of women may not like to give their exact age. So sometimes we need to use categories just so that we get data. So missing data can be an issue that we need to consider when we're designing a study. So I'm going to talk about 2 different types of statistical techniques: the nice, straightforward descriptive stats, and then the inferential stats that you'll typically see written up in many research papers. So descriptive stats can make up about 90% of any paper. You might use it for checking for errors or outer range values. Certainly you should be using it for describing the sample. Some research questions can just be easily answered using descriptive stats. But another important part is also looking at the characteristics of the data to see whether some of those inferential statistics that we might want to use are appropriate. So just quickly go through this. This is fairly straightforward. So when you've got categorical variables, your descriptive statistics might consist of just frequencies and percentages. At a slightly more sophisticated level, there might be a cross-tabulation, where in this example, for instance, we're just looking at the number of male and female respondents who are smokers or not smokers. So we can just report the percentages there. So we're not doing anything fancy. We're not inferring anything from our sample to a population. We're just describing what we see in our data. When we have continuous variables, there's two types of stats we typically report. The sophisticated name is measures of central tendency, but basically we're just talking about a mean, a median, or a mode. So we're looking at describing the centre or the middle value of a set of numbers, and it's a point at which our values cluster on either side. So we're just looking to describe the middle point. Now, it does depend on the nature of your data. If you've got nice, normally distributed variables, I love the word normally distributed because there's nothing normal about it, certainly in the psychology world. Many of the characteristics don't show this nice bell-shaped curve. But if it does look like that, then the mean or the average is appropriate. But if you've got skewed data, skewed meaning tipped over to the left or the right or lumpy, then the mean is not appropriate, and we need to use the median, which is basically the 50th percentile. And that's a mistake that I do see a lot of researchers just relying on mean values. But mean is very much affected by outliers and other issues to do with the distribution. Okay, so the other characteristic we look at describing is measures of dispersion, which basically is how closely the scores cluster around that midpoint, be it a median or a mean. So the two most common ones we see are standard deviation for those nice normally distributed variables and the interquartile range, the IQR, when our variables are not normally distributed. So basically we're looking at how stretched out our variables are. Are they all clustering together or are they spreading themselves out? Because that makes a big difference in terms of the statistical tests that we'll use later on. So if we have a look at those two measures of dispersion, so standard deviation is only suitable when we have a normally distributed variable, because what we're wanting to do is look at where the mean is and then be able to have these indicators of how spread out the data is. When our variables are skewed, what's more appropriate is this thing called the interquartile range, which is fancy speak for the 25th percentile and the 75th percentile. So we would report this in the context of the median, which would be the 50th percentile. So we can actually get a feeling for how spread out our data is by looking at those values. Okay, so we're going to move on to the inferential statistics now, which are the ones that basically we're using to sort of tell more complicated stories. And unfortunately, people get very hung up about inferential stats, you know, is it statistically significant? And sometimes they lose sight of the story that we're trying to tell. So what we're trying to tell with inferential statistics is, so we've taken a sample, this ladle of soup, and we want to know whether the findings that we obtained using the sample actually reflect what's really going on in the population as a whole. Or could it just be random? You know, that we could have scooped in an area where there wasn't many carrots, for instance, for using the soup analogy. So we want to know how much confidence we can have from taking the information we've got about our sample and making or inferring what's happening in a population or a larger group. So to do that, we use hypothesis testing, obviously very based in a scientific framework. So it's a bit like fronting up for court and looking at, is there enough evidence to support your case? So we propose a null hypothesis and an alternative hypothesis. And the null hypothesis is sort of like assuming a person's innocent until proven guilty. So our null hypothesis assumes there's actually no difference between the groups that we might be interested in, or there's no association between variables. So that's our starting point. So then we propose an alternative hypothesis where we say, okay, there is a difference. We believe there is a difference between the groups, or there's an association between the variables. And we're just going to collect evidence and we're going to weigh that up. We can't ever prove the alternative hypothesis. You know, we can't prove that group A and group B are different. But what we can do is collect enough data that suggests that the null hypothesis, that is the groups are not different, is just so unlikely given our results that the alternative explanation that there is genuinely a difference between group A and group B is the most likely explanation, but it's all based in probability. Okay, so let's look at this thing called statistical significance, which is where our tests come in. So if I designed a new way of teaching statistics and wanted to see if it was effective, I would obviously collect data where I expose my students to an exam which tests their statistical knowledge. Perhaps I should have done that at the start of this presentation, given you a test. That would have scared a few people off. So we look at basically your level of understanding before you did the program and your level of understanding after we did the program. So I'm being very optimistic here. I'm saying your score at time 1 beforehand might have been 10. And afterwards, after all my amazing teaching, the score is 20. So are we excited? Well, yeah. And I think it's important we actually look at the results before we even do any statistical tests and just go, oh, yeah, actually, if that happened, if the average score was 10 and I got everybody up to the average to 20, yes, I would have been fairly happy with that process. But we can't just go on whether we like the results. We need to test it against this convention, p less than 0.05. So we're talking probability. We're looking at the probability of the results that we obtained, or even more extreme, was actually true. Sorry, if the null hypothesis were actually true, what's the probability of us finding a 10-point difference? Could that 10-point difference that we got just be due to chance, just random variation? Okay. So what we're looking at, I'll just put a graphic there to remind you that we've got a distribution of scores at time 1, and we've got a distribution of scores at time 2. So even though we're talking about a mean or an average, a single value, we're actually measuring it across the whole group, okay? So this is what I'd like my results to look like. That is, you can see that the scores, you know, a fair way away, and that the distributions are not just one big lump. It's a very scientific term, one big lump. So we use an inferential statistical test, in this case, a t-test, t for 2, to calculate the p-value. So if the probability value is less than 0.05, then we can say that the result is statistically significant. So translated, it means there's less than a 5% chance that the 10-point difference we found was just due to random variation. So given random variation, a 10-point difference in the two measures is really unlikely. So the other alternative explanation is that intervention, the treatment, whatever you're looking at, was effective in changing scores. So that's what we're looking at. Now, this is the bit that I find drives students nuts, because you've got all these little fractions, you know, 0.05, and we're talking about p less than 0.05. So what does a number less than 0.05 look like? Well, it looks like a 0.04 or a 0.01 or a 0.001. So I have a little cheat sheet for students to interpret their p-values, because people don't necessarily think with those values. So if the number's one of those sort of numbers, then you'd be pretty happy, because the result you obtained is probably not due to chance, and that whatever you're doing to improve your teaching has significantly changed the scores for people. Now, sadly, if the p-value you get is 0.05 or 0.06 or 0.10, values like that, then we can't be sure that random variation hadn't occurred. So we can't really be confident that our new technique has been proven to be successful. Now, that's a pretty tough ask. You know, like sometimes you'll run an intervention and you'll see that a lot of people improve. But if you don't actually meet those criteria, the convention when you're publishing, of course, is to say it's not statistically significant. Now, getting something to be statistically significant is not the be-all and the end-all. And I see students get really excited. Look, I got a p less than 0.04, right, for instance. But it doesn't mean that's important. It doesn't mean that it's large enough to be practically significant. It doesn't mean that you would then roll this intervention out to all schools and all children. We need to look at a couple of other things. We need to look at something called the effect size statistic. So that's looking at how big an impact it's had. So if the intervention only improved people's scores by 2 points, is it worth it? Okay, is it practical to run a program when there's only a 2-point difference? So we need to really understand that statistical significance is only a very small part of the process. So just going on to the next bit. How can we influence whether our results are statistically significant? Well, the main one is sample size. So the larger the sample you have, the more people you go out and do research on, the more you can trust the results you get, okay? Because it's a more accurate representation of the population. When you have small samples, you can end up with a bunch of quite weird people in your sample, and that can corrupt your results. So we want large samples that really give a good cross-section of the population that we're trying to infer to. So if you're only looking at 20 students, the odds of you getting a statistically significant result is pretty slim. If you're getting up to 200 students, you've got a better chance of being able to detect that. So note to self, try and use large samples. The other thing that can make it more likely that we're successful in our results is to actually have an effective intervention that does make a change. Right? So it seems to make sense that if you want to change people's scores, then you should do something that will change people's scores. So this is where things like pilot tests and things can come in, that you're really refining whatever intervention or approach you're using, design it well, test it well, experiment well, get people's feedback. And this is where qualitative research really comes into its own. So for a lot of the quantitative studies that I've done, I've always done a qualitative study beforehand, just to really make sure that we're understanding the experience of the people that we're going to be investigating. And if we can understand what's important to them, you know, like if I ask you guys, if you were needing to learn statistics, what is it that's important to you? What do you find confusing? What approach would you like us to take? So qualitative research has always been the underpinning of a lot of the work that I've done. A lot of my own personal work has been in the area of stress. Now, all of my earlier studies were initially looking at what does stress feel like for people? What are the factors that contribute? What are the major sources of stress? But after doing that initial qualitative research, then you can start looking at quantifying some of it so that you can take that research with a smaller group and look at its implications for the larger group. So the more you understand an area, the better designed your intervention or whatever can be. The other thing that it can improve your chances of getting a statistical result is just how much the characteristic varies in the groups you're looking at. And this is why drug companies, when they're testing new drugs, they actually test it on a really, really narrow definition of their participants. So for many drug trials, they only use males. They only use males between 18 and 35. And they only use males that have a certain set of characteristics, which means that they have a really narrow band, if you like. If you have a very sort of large, diverse background, so for instance, for you guys, in the audience, there'll be people who know nothing about stats. There'll be people who know moderate amounts, and there'll be people who know a lot. And if I was assessing your knowledge after this talk, those of you who already had a good background of knowledge in stats wouldn't change. So my intervention wouldn't have any real effect on their scores. So if I was designing a study, I wouldn't mix people's level of stats knowledge within the sample. I would say I'm going to target people who have very low levels of knowledge, and I'm going to see if I can improve them. So just defining more narrowly the group that you're targeting can actually improve your results. Because if there's no room for people to change, because they're already at the high end, they can't change. So you're just shooting yourself in the foot by doing research with a really broad range of scores at time one. So the research design, I think, is probably one of the most important things. Maybe before I taught this stats course, we should have talked about research design and how that can really make or break the effectiveness, because unless you design your study well, the stats are not going to save you. So if we have larger samples, if we have random samples where there's no bias, if we avoid confounding variables, that is, the two groups we're looking at don't differ in terms of socioeconomic status or location or other factors that might confound. And whatever we're using to actually do the measuring, the test, the scoring, it needs to be reliable. Okay, so assuming you've got good data, now we need to choose our statistical test to use. And this is horrible. For so many students, this is the bit where they just go, no, there's too many. I don't know which one I should use. It's actually straightforward. Once you know your research question, what you've got is your ingredients in terms of your variables, and that you've checked your data for its suitability, there's really not many choices. So let's have a look at the type of research question. We might be interested in exploring relationships amongst variables. So, for example, is there a difference between students? Is there an association between students' anxiety and their performance on a test? Or we might be comparing groups. So we might be looking at, do male and female teachers differ in their levels of reported burnout? So once again, you just define your research question, and you now have a look at your measurement level. Have you got categorical variables or continuous variables? That will narrow down the choices that you have. In terms of study design, are you repeating the same measure across time on the same group of people, or are you comparing totally different people like males or females? Is your data nice, normal, distributed interval level data, or is it a bit skewed or lumpy or bumpy? If you've got lumpy, bumpy data, you'd use a non-parametric test. If you've got a nice, normal, distributed, and you've met a lot of the assumptions that the tests make, you would use the more powerful parametric tests. So once we've decided whether we're exploring relationships or comparing groups, there's really just a smorgasbord, and the test that you're thinking of using will vary according to the nature of the variables that you have. So here are some of the techniques that will allow you to explore relationships. And they're sort of ordered in terms of their complexity. So by the time we get down to structural equation modelling, yeah, I think most people's heads are spinning. Don't go there first. So chi-square is probably the simplest association. We might be looking at, is there an association between sex and smoking status? There's our nice familiar crosstabs. And we can just add an extra statistic to say, is this finding, the difference between 25% and 40%, is that statistically significant? Is it unusual enough to have not occurred by chance? So we would just use the chi-square test. If we have continuous variables, we can use one of the correlational techniques. And there's two flavors. There's the Pearson correlation, which is the nice normal distributive variables, and then the lumpy-dumpy data, you'd use the Spearman rank order. But basically, we're just looking at the association between two variables. And does it look like there's a nice even pattern? As one variable gets higher or increases, does the other as well? We can also look at both a positive and a negative relationship. We get a nice number that tells us the strength, and we get the negative, which tells us the direction. Then there's some guidelines for being able to interpret how big is big. Well, if you've got a 0.7, you'd be very, very happy because that's a large correlation or a strong association. If you're down at the 0.1 to 0.29, no, not really. When we move on to partial correlation, we're still looking at association. So there's a strong correlation between the number of grey hairs somebody has and the health complaints that they report, okay? So everyone's going to rush out and dye their hair. Well, no, because what we've got is a confounding variable. We've got a variable is actually the underlying cause of both of these. As we get older, number of grey hairs increase, and so do our health complaints. So if we use partial correlation, we can test for the independent relationship here after controlling for our confounding variable. So it just takes that level, analysis to the next level. So moving on, something called model regression basically allows us to look at a set of continuous variables and their impact. So my research looked at how do these various characteristics, sense of control, optimism, and social support, how well do they predict a person's stress level? Well, the answer's pretty well, actually. If we have a categorical outcome, so the likelihood that a teacher is going to resign in the next 5 years, we can actually put in a set of categorical or continuous. So we can include sex, which is obviously a categorical variable. We can also include blocks of variables. In this case, we've got these various personality type characteristics. Structural equation modelling just takes it a whole next level where we can actually look at both the direct and indirect relationships. So we can see what direct effect our variable has, but also how it works, what's its mechanism. So as we feel out of control, that increases our stress level, which increases our likelihood of developing depression. And structural equation modelling just allows us to explore each of those indirect and direct effects. So it's great fun. You actually just draw a diagram, chuck it into the program, and they come back with little numbers on them telling you whether there is an association. So they were all relationship type statistics. When we're comparing groups, though, we've got another set. And they have fancy sounding names, one-way analysis of variance or multivariate ANOVAs. But it's not very complicated as we're going through to know which one to use. So we've got a set of t-tests. T just means that we're looking at two things. So the t-test for independent samples compares group 1, group 2. In this case, we might be looking at males and females and their stress levels. And it allows us to compare two separate groups on one continuous measure. So that's our ingredients, if you like. So if your data matches that, that's the test you'd use. If you followed people, the same group, over time, perhaps with an intervention in the middle, then the test you'd use is a t-test for paired samples. Paired just means that it's the same people, time 1 and time 2. So that's a pretty easy decision to make once you know what your research design is. Now, a fancy name, analysis of variance, it's just a t-test that's been extended to add an extra group or an extra time point. So it's exactly the same. So something called a between groups ANOVA, you might be looking at the stress levels of teachers at school 1, school 2 and school 3. So we're just adding an extra group there. So once again, we have separate groups and we have a continuous measure as our outcome. And for our repeated measures ANOVA, 3 time points, same people, same measure. Now this is where it gets interesting. If you want to throw a few extra variables in and look at their interaction, then a 2-way ANOVA is what you'd use. This is actually an example from some of my research. So I've got 2 categorical variables. I've got sex and I've got age categorized into 5 groups. And my outcome is stress. And this graph shows that there's an interaction effect. That is, if we look at the level of stress for the different age groups, it's different if you're a male than if you're a female. And this is what I like about these sorts of research. You can find results that you weren't anticipating. And this is not one that I was anticipating. Okay. So that can lead to more research questions and further research. Now, there's this nasty looking thing called a multivariate analysis of variance. All it is you're just comparing 2 or more groups, but you're not comparing them on one thing. You're saying, let's have a look at their stress levels, let's have a look at their anxiety levels, let's have a look at their depression levels. And this is a more sophisticated design because you're not just looking at the impact of in this case, sex, on just one thing. You're looking at it as a sort of part of a constellation. So that's just called a multivariate, meaning that our dependent variable, there's actually 3 of them. Now, this would work in schools. You might be looking at a child's performance in English, maths and science. So you might look at them as an integrated whole first in terms of academic achievement, but you can always then separate them out and see if it's only for maths that you're seeing a difference between, classes. So the data analysis process really just needs some very careful thought and planning, some good tools, and necessary skills to not only design the study, but also to analyse and to use the stats appropriately. So if anyone who's done any research, it's actually quite a long process from that initial set of research questions right through until you're collecting your data, you're doing your analyses, you're getting all your results, you're reporting them and you're getting them published. And at each step along the way, obviously there's decisions to be made and knowledge that you need. So one of the pieces of knowledge and one of the skills you need is SPSS. Because if you're going to do statistical analyses, you need a good tool. And SPSS is, in my opinion, and many others, one of the best tools. Please do not use Excel. You cannot use Excel for statistical analyses. It is a disaster. I have seen the results that people, even just adding up scores, when there's missing values, SPSS just treats it like, oh, that's a 0, I'll just add it up anyway. SPSS idiot proofs some of those fatal errors. So please, if you are thinking of doing it, use SPSS because it's much faster, easier, more reliable. There's a bit of a learning curve, okay? But basically it's a spreadsheet with nice drop-down menus that you can use. You're not having to do anything. There's no coding, there's no maths. You're just selecting variables by putting things in a box and choosing what you want. So it's far less scary than people think when they first start. Interpreting the results, okay, it's a matter of just knowing how to read the output and how to generate graphs, because graphs helps you visualize the data and the results. The numbers are only a small part of that process. So here's my advertisement coming to the end. I wrote a book on SPSS over 25 years ago for my students. It's currently available in its 7th edition. Best place to get it is Amazon. It's on special at the moment. But I've just written the 8th edition, which is with the publisher. It'll be out early next year. But the idea with this is it literally is the Bible. It just takes you through everything you need. I basically hold your hand and say, okay, let's go through setting up the data file. Let's screen and clean the data and make sure there's no errors. Let's go through that descriptive phase of getting to know our data. Manipulating it, we might need to cut our age variable into categories. SPSS does all of that for you. I've got a chapter on choosing the right statistic. And obviously each of these techniques that I've talked about, I go step by step. What are the options? Which one should you pick? How are you supposed to actually run them and interpret the output? Is don't try and do it on your own. I think when you get output, it can be pretty overwhelming and you need someone to say, look at this number, not that number. This is what this means. The other thing that I put into my book was I actually showed people how to write the results up as if it was going into a thesis or a journal article. And it's interesting because I was the first to do that. And every other book now that's ever been published is including those samples. I think that's why mine gets cited, because I actually give people, I guess if you're cooking a pavlova, it shows you how you might present the pavlova so it looks nice. Well, in this case, it's how to present the results, that messy mix of numbers, in the way that'll get you published, because there are conventions, there's ways that journals require you to write statistics. So I just show you, here's the number here, this is where we put it, and this is how you express it. So the idea was just to be something to help students go through that process. Okay, so I'm still within time. So I'm hoping that helped to some extent just take away some of the mystery of the underpinnings of statistics. And I certainly wish everybody who's ever doing research the best of luck, because you are significant.